As we are, thank you. As we're getting closer to celebrating World Water Day, which will be on March 22nd, that is an event that the United Nations has pulled together to help all of us across this world take a look at the lens of just how special a planet we live on, the water planet that allows us, enables us to have life as we know it, which requires having water, and in many cases, fresh water. So we're coming together this evening to learn more about Earth's most precious resource, and that is our fresh water. Tonight, we have an incredibly talented bench of people who are going to be talking to us. We're going to be starting off with Dr. John Bolten. He is the Chief of Hydrological Sciences Laboratory at NASA's Goddard Space Flight Center, and he is currently serving as the Associate Program Manager of Water Resources for the NASA Applied Sciences program. He's also leading NASA's International Water Strategy. After John, we will have Dr. Chris Kidd. He is a research scientist with the Global Precipitation Measurement Mission, and his research interests lie in the field of Earth observations, particularly with satellite meteorology and climatology. After Chris, we will have Marilé Colón Robles. She is a project scientist for NASA's Globe Clouds and is an education and outreach coordinator at NASA Langley Research Center with the Science Systems and Association. And then we will finish up with Noah Newman. He's the research coordinator for CoCoRaHS, which is the Colorado Climate Center and Education and Outreach Coordinator for the Community Collective on Rain, Hail, and Snow Network. All right, without further ado, Dr. John Bolten, I will turn it over to you. Thank you.
Thank you, Dorian. Let's see, I will share my screen.
And I will wait and let you know when I'm seeing it and seeing it in the right view. All right, you're great. Good stuff.
Okay. Hey, thank you so much. What an honor to be here. And this is a very impressive group. Dorian, thank you so much for the introduction. I'm just going to get right into it. I love your introduction there talking about water. We are on the water planet. So what I'm going to do today is just give a sort of an overview of my relationship to water, how I got here. These are pictures of me. I'm from rural West Virginia. I grew up near Parkersburg, and I grew up on the water. This is my backyard. And that kind of guided my career and my entire path. That's how I got here. And sort of the theme of my talk is that how water influences us. And I've broken this talk into a few things with sensors, science, and society. And right in the heart of that is water and GPM. So it's very neat. So if we go back and we think of how water relates to us, this is the picture of the Indus Valley 5,000 years ago. So this is a cartoon capturing this. Thinking about how societies meet water needs. It's a perpetual task, whether it's for transportation, for agriculture, for farming, but it really plays a formative role in the development of those civilizations. This has not changed today. 5,000 years later, it's the same thing. We have very similar struggles. Where we build cities and how we transport, etc., is solely based on our access to water. If we fast forward a few years, this is Marcus Vitruvius. I think this is in 1400, or no, this is the first century BC. And he was one of the first folks. He was to look at how observations can be collected and sort of tell a story of our world. And he was very interested in water. So he kind of played a critical role in looking at how observations can inform our understanding, especially related to water. He was watching where the rain fell and how this there was a response in stream flow, for example. Now, if we fast forward a few more years and we look at this, we have this concept of, this is sort of an evolution of hydrologic understanding, if you will. But what more importantly, it's bounded by technological opportunities and societal needs. And why this is so interesting is we're seeing this evolution from flood design on the bottom all the way up to climate change, water quality, and human footprint. So our understanding is continuing to evolve, but it's based on observations. And that's sort of the theme of this presentation. So as we're bounded by technological opportunities and societal needs, that doesn't change. Now, this guy, he definitely knew this. This is Leonardo da Vinci. And he was a very, very busy man. But what he was doing here, he had this device and he was measuring stream flow. So if you look at this picture, he was measuring and racing someone would throw a ball in the stream and he would walk beside it and he would measure the velocity of the stream. And Da Vinci did several interesting things related to the water cycle. I remember the water science. In fact, he came up with one of the first first concepts of the cycling of water in the world. And it was based on these observations that he had. If we fast forward a few million or a few hundred years, this is Edmund Halley in 1692. So he's famous for a number of reasons, but you may know him because he predicted the return of a comet that shares his name. But it's something he also did is he came up with this concept here of the hydrologic cycle as he saw it. Now it was not perfect, it wasn't correct, but it was based from logical observations. And this was very, very interesting. So he was obviously very, very good at taking observations, very good at making predictions. And so he used this to make predictions of water change. This gentleman here is Leroy Sherman. So if we fast forward a few hundred more years, Leroy Sherman, what we're seeing here is a hydrograph. And this hydrograph, to this day, it's still one of the most foundational concepts of hydrology. This is a way of sort of relating a catchment behavior. And what it does, it relates rainfall to stream flow response. And this is based on Dr. Sherman's observations that he took. And he was really able to move away from qualitative to a quantitative assessment of hydrology. And this is kind of a game changer. Now, this is a fun one here. In the chat, if anyone has a guess of what this picture is, you will be celebrated by people clapping for you. This is the first image of planet Earth ever taken. So this was taken in December 24th, 1964. And this was the folks took a black and white camera and they put it on a Delta II rocket. And they got lucky because the camera took a picture of this, and what we see is clouds. It was funny because when this picture was taken, they are actually a little bit upset that they got like, oh, these clouds are all in the way. We can't see the land surface. But we know now that clouds is where it's at. It's all about water, in my opinion, anyway. So that year, or 1942, is also very interesting, and because it was the first year of the ENIAC computer. And this ENIAC computer was a room-sized computer that right now, if you see my iPhone here, this iPhone here is more than 230 million times faster than this room-sized computer. So if you think of that, just 78 years later from this computer to the cell phone, the way we collect data, the way we see the world is changing. And this is obvious here. This is Moglen and Bross from 1994. Now this, we were able to leverage computers and graphic visualization of our observations and our science. This was also a game changer, and it sort of demanded a rethinking of how we visualize data and how we go from this data poor to data rich environment. And I love this picture. This is from the inauguration of 2005 and 2013. These events were observed entirely differently, just a few years apart. So in the same way, the way that we observe the world is changing. This is the most iconic image ever taken. This is the most reproduced image in human history. So this is December 7th, 1972, when the astronauts from Apollo 17 were on their way to the moon, and they turned around and they took a photograph of the Earth. And as Dorian said when we started, this is the water planet. This is the pale blue dot here. And if we move on to the next portion of the presentation, talking about sensors. So in just 78 years, we've gone from this grainy black and white photograph to an entire suite, a constellation of satellites. And these are just NASA's Earth observing fleet. So we have more than 20 satellites that are observing different parts of that hydrologic cycle. The same hydrologic cycle that Leroy Sherman was looking at, the M and Halley that Leonardo da Vinci were trying to observe by throwing balls in the stream and racing them down the road. So now we went from this black and white photograph to being able to tell the height of a reservoir within the accuracy of 3 centimeters from a satellite hundreds of kilometers in space. It still blows my mind that we can do all these things. And this yellow circle here is GPM, and it's very exciting. In 10 years, we've gone from this game-changing science of GPM, being able to measure precipitation all over the world at an unprecedented spatial and temporal resolution, as I'm showing here. This is the Hurricane Ian in 2022. And it's just really neat because in hydrology, it all really starts, and it really comes down to precipitation and being able to characterize precipitation events at an unprecedented value or in an unprecedented way really has changed the way that we are able to characterize, understand, and predict hydrologic events. It's very, very neat. So this is a kind of a fun picture. This is by Dennis Lettmeyer, and I added a little bit at the end. But what this is showing, this is the number of publications in water resources research with the terms remote sensing or satellite in the title. So it's kind of telling, and you can see this evolution over time. So just in a short amount of time, people are catching on. They're really understanding that using this vantage point from space, we're able to have really good understanding of how the world works. And I can only imagine what Leonardo would have done if he had access to satellites we do today. It would be pretty crazy. So what we're seeing when we look at the Earth using these satellite observations, we're able to really have a better understanding of how the world works and our relationship to water, and that's what I'm particularly interested in. But what we're seeing here, this is work by Matt Rodell and Bai-Ling Lee at NASA Goddard Space Flight Center. So they just published this in Nature Water this year or late last year. But what you're seeing here, this is sort of capturing the global intensity of extreme events on the planet, and you may understand that there's this relationship between INSO observations, so sort of the temperature changes on the Earth and how these are related to temperature or to global extremes. But what we're seeing is the total intensity of wet and dry extremes is actually correlated with temperature more than these INSO or climatic oscillation events. So this is not as a hand wavy result. This is based in observations from a suite of satellites. So it's really helping tell the story of climate change. This is a pretty interesting slide. This is from Dr. Sujay Kumar at NASA Goddard Space Flight Center. And we're understanding that to understand our planet, we can't look at it just through the lens of water, even. We can't look at it just through the lens of greenhouse gas or sea level rise. You have to look at this from a system of systems. And that's what the Earth Information System, or EIS, is doing. So this is sort of a transdisciplinary collaborative research application activity where we are working with folks who are experts in greenhouse gas and fire and agriculture and crops. And we're trying to get a better understanding of our changing planet by pulling all of these systems together, leveraging the satellite observations, and most importantly, by developing land surface hydrologic models and other Earth system models that can be constrained using these observations from space. So I'm going to show a couple examples from the EIS team and what they're doing. This is a paper by Wanshu Ne that was just recently published. And what they're using is these blended observations to assess changes in the water cycle. And what we're seeing this, the shifting of seasonality and changes in extremes. And why this is important is if you base your science on trend analysis, for example, if you develop a climatology from observations, we're seeing the climate is shifting, the climate is changing. So we're seeing hot spots of trends and these changes in extremes, and essentially a shifting of the seasonality. And this is a very, very interesting finding, and it's relevant to everyone here. And I think we're going to hear a lot more about this. But the way they did this was by blending observations from GPM, from SMAP, MODIS, and GRACE. Very, very cool stuff. So another thing that's interesting here. So these figures, basically red is drier times of dryness, blue are wetter times. These are all, this is in the Northwest. So there were two major drought events in 2016 and 2017. And these drought events led to billions of dollars in economic loss from the United States from agriculture alone. Now there can be a drought because of a deficit of precipitation or evaporative demand. And so if it's very hot, you'll also lose water. Both of these things result in similar effects, where in this case it would be a lack or anomaly of soil moisture, and your crops will dry out and die, and your yield will be reduced. But what we're doing here, we're showing this evolution of drought by combining blended observations. And what's really neat about this whole thing is being able to assess and predict and sort of mitigate these extreme events that we're seeing. And this is very, very, very important. And I think I have one more thing. This is interesting. This is by Kerry Voyevich at NASA Goddard Space Flight Center. And what you're seeing here, the colors represent areas of what we call the world's water towers. So these are areas where water is captured by snow water equivalent in snow. And so we're trying to look at these water resources, where the water towers of the world are. And what's interesting about this is when water is captured in snow, it can be captured for season after it falls, essentially, but it travels across political boundaries. And so these transboundary watersheds, essentially transboundary water storages, are relevant to a lot of folks. And in many areas of the world that are water insecure and food insecure, they share these resources. And this is where NASA is supporting these efforts by providing opportunities for, by leveraging the satellite observations, combining them in a meaningful way by integrating them into land surface hydrology models and other Earth system models for helping inform these water resource management strategies. This last one's kind of cool. This is using observations from the Soil Moisture Active Passive mission. This is by Manhun Lei at NASA Goddard Space Flight Center. And essentially, we're able to forecast future vegetation health changes. We're seeing NDVI, which stands for the Normalized Difference Vegetation Index. And we realized that there is this relationship between soil moisture in the ground and the health of vegetation. And we're using this to forecast future NDVI and future agricultural yield. And why this is important is that the USDA National Agricultural Statistical Service, or NASS, they use this similar approach for NDVI for estimating how much yield is captured in the crops. So we're working with many partners around the world to do that. And this brings me to my last topic of society. I think everyone here, you tune in probably because you understand that water is important. But if you just look at some of the headlines here, we're seeing that there's calls for increased water security, how water is related to foreign policy, how there is transboundary water is particularly important. And this was also captured in the U.S. Global Water Strategy of the U.S. government. And we see that the water is the #1 threat multiplier in the world. And we're seeing that it is becoming more and more important. And something I like to say that by the time my daughter is my age, there will be nearly 10 billion people on this planet. When I was born, there were 4.7 people on this planet. So in one generation, there was a doubling of the human population. And this is important, especially because we need to find a way of sustaining these populations through food security and water security. So our relationship to water is changing drastically. This brings me to this last topic, and this is how NASA is working with the NASA Earth Action Program, where we are working with partners around the world to help inform their water decision support systems and decision-making capabilities. So we're trying to go from data to decision-making. It's very, very exciting. And these capacity building efforts really require a lot of teamwork and a lot of brighter minds than mine coming together and working with folks. And what we're seeing here, these are pictures from the Mekong River decision support system that we were working with NASA's Earth Action Program. And we came together, we found solutions that were relevant for their decision support systems in the Mekong River, which is supporting nearly 10 million people as their main protein source. So this was a pretty interesting thing. And if you're curious, check out this paper by Ibrahim Muhammad and myself and others at NASA Goddard Space Flight Center, where we looked at how climate change how we can inform future water governance, looking at different climate change scenarios and sort of looking at a current business as usual approach and combining this with a future approach. But the message here on the left is kind of a confusing plot, but we're seeing that the future scenarios require a rethinking of reservoir storage for hydropower dams. And this is very, very important because there are a lot of dams in this area and a lot of people. There are 5 countries that depend on the Mekong River in many, many ways. And so this was great because we worked with Conservation International and we worked with a lot of the water agencies in the region to have a better understanding and learn from them about their needs and capabilities for adapting to these future changes. And these are some photos of us working in Argentina in 2022 doing the same thing. And I think I have, oh yeah, here's one. We did a needs assessment. There's a big one theme of this talk is learning from regional partners and gaining an understanding of what they need. And what you see here, these word clouds, show sort of their short-term and long-term goals. And if you look really closely, you can see that they're looking for training and support with knowledge processing and data processing. And long-term goals include support with hydrological modeling and data development and project planning. So we took this, and just last week, if I look a little tired, this is because we were in Brazil and Argentina, or Brazil and Paraguay last week, and we had a meeting in the Itaipu Dam. This is with the CIC La Plata group and supported by the Organization of American States and our friends at Army Corps. I thought it was pretty cool. This what you're seeing here is a giant, one of the world's largest. It is the world's largest source of hydropower in the world. So the Itaipu binational dam, we're all here, and we got together and we developed solutions based on what we learned in the previous things. And this was all based on NASA satellite observations and modeling capabilities. I also wanted to show a picture of capybara. I finally got to see a capybara in person. It was awesome. And yeah, so bringing it all back to the Indus Valley. Really, very little has changed in regard to our need for water and understanding how to manage water better. And I'd like to remind you all of that. So thank you so much for your time. I look forward to the next discussions. And Dr. Chris Kidd is going to follow up on more detail on the nuts and bolts and the nitty gritty of GPM. So thank you very much. And I would like to give a shout out to all the folks who did the hard work and heavy lifting for this research. Thank you very much. And I look forward to answering your questions.
John, thank you so much. It is truly just this seems like a big world, and I think we've seen with technology and going through going through COVID, what a small world indeed it truly is. As I'm looking at the people who are joining us tonight, what a great group of people from all around the world we have. And indeed, our very peace and our life and security depends on being able to access water. So thank you for your insight. Thank you for going back in history, taking us to the present time, showing us some of the ways in which these data are used, not just for research purposes, but for real world applications, because kind of at the end of the day, that's so much of what it's all about. So we very much appreciate it.
Thank you, Dorian. Appreciate it.
And if we have people, if anyone has questions for Dr. Bolten, if you'll put them in the chat, and we're going to go ahead and move on to Dr. Chris Kidd. Thank you so much.
Hello, good evening. Okay, let me share my screen. Hopefully should be here somewhere.
Marvelous. And I will let you know when we're good.
Okay. Let's see if we can get it to full screen. Okay, should be full screen.
Brilliant. Thank you so much.
Marvelous. Okay, so I'm just going to be sort of talking about how the Global Precipitation Measurement Mission actually measures precipitation, how we use satellite observations to measure precipitation on a global basis. And it's worth just thinking about how we might actually measure precipitation to begin with. I mean, there are many different ways. I mean, one of the simplest thing is just a tin can. I mean, you just put it out in the rain. The problem is that you have to keep measuring, you have to keep going out, taking measurements, things like that. So clearly you want to automate it. Of course, you have fun things like sort of a pair of wellies here with sort of the rain level on, not terribly accurate, of course, or as we'd probably say in England, a Heath Robinson sort of measurement device which collects water and ends up sort of ending up in a bucket at the bottom. But of course, to do it properly, you need to have proper rain gauges. And obviously we'll hear about a bit more about this in a moment from Noah with the CoCoRaHS network. But if you look at the sort of real-time gauge data that goes into a lot of the sort of meteorological organizations for input into meteorological models, things like that, the actual distribution is actually very, very poor, as you can see in the map in the center there. And certainly over the oceans, we really do not have very much information at all. And in fact, if you collected all of those rain gauges together, you actually end up with sort of very, very few sort of gauges reporting. It's about 20,000 rain gauges worldwide reporting in real time. And they would all fit within the sort of about half the center circle of a sort of football or soccer field. So we're trying to measure global precipitation with a very limited set of data. And even if we add the weather radars, they tend to duplicate a lot of the sort of rain gauge networks. However, gauges are important for global precipitation because they actually are the most direct measure. However, satellites can provide consistent, regular observations with global coverage and real-time delivery of the actual data they collect. So how do we actually observe precipitation from satellites? Well, if you take this sort of cloud image on the right-hand side, first of all, we can use visible imagery. And this relies upon light being reflected off the actual clouds themselves. Now, of course, with it being visible, you can actually only use this during daylight. At night time, it's not really much help at all. There's infrared measurements, which actually measure the temperatures of the cloud tops. And typically, the colder the cloud, the deeper the cloud is, and therefore the more likely it is to precipitate. But again, it is really just measuring what there is at the top of clouds. If you go into the passive microwave, then we're looking at natural emissions from the surface, but also from the raindrops themselves within the clouds. And of course, if we take something like active microwave or radar, this relies upon a backscatter of radiation from the hydrometeors, the precipitation particles within the cloud. So you can see that the microwave sort of radiation is actually far more direct than the visible or infrared. And you can sort of see this in this next image here. On the left-hand side, we have a visible image over Europe, and you can see there's a whole range of clouds there, which show up quite nicely. The problem is knowing which of those clouds are raining. Now, of course, we can look at the thermal infrared. Now, the image you see there is probably not terribly familiar because that is what the actual satellite sees. Normally what we do, we actually invert the image so that the clouds look white. And there we get a bit more differentiation. We can see that some of those clouds are a lot brighter, meaning they're colder and more likely to precipitate. But again, the problem is cloud tops versus surface rainfall can be quite different. So what you need is something like the GPM mission. And the GPM mission is important because it contains both an actual microwave imager, which senses the passive emissions from the hydrometeors, and also an active sensor, which measures the backscatter from those particles. And so between those two instruments, you can get a far better measure of the actual rainfall that's occurring near the Earth's surface. And in fact, if you look at the frequencies of the passive microwave, here you've got a sequence going from the 10 gigahertz right through to 183. You can see how those different frequency bands observe the atmosphere, the surface slightly differently. On the far left, you can see that the oceans, here we have the Mediterranean, which show quite dark. The land shows up fairly bright. Over the oceans, we have emissions from the actual water droplets. And so there you can actually see how the sort of rainfall, excuse me, is actually adding to that radiation, and we can actually sense where that rainfall is occurring. In addition, at the higher frequencies, we get scattering from the atmospheric ice, the tops of the clouds. And so we can actually see the sort of where those clouds are over the land areas. One of the problems, though, that right down at the bottom end at the 10 gigahertz, all those bright spots, that's radio frequency interference. That's from when people are using their phones, communication systems, things like that, and they can interfere with some of the satellite measurements. Now, of course, one of the reasons why we do this is for actually measuring storms. And hurricanes, of course, are one of the sort of major storms, particularly in the US. And here we have a sequence of images from the GMI, from the 10 gigahertz through to the 89, showing how it responds to these different channels. And on the right-hand side, we've actually got a rainfall estimate from those particular channels. And one of the key things is that the GPM mission alone can't observe precipitation globally all the time by itself. So we have a constellation of different sensors that actually sort of allow us to observe the whole of the Earth's surface at least about once every 3 hours. And we bring all of those estimates together, and we actually are able to combine them to provide rainfall globally at a daily or finer resolution. And one of the sort of ultimate products from the GPM mission is what we call the iMerge product, the integrated multi-satellite retrievals for GPM, as we can see here. And this provides us with 30-minute estimates of global precipitation in a very near real-time situation. And if you want to actually have a look at a loop of the last week's iMerge, the link is there, and I'll also put that in the chat as well if you want to have a look at that. So I'm happy to answer any questions later if time permits.
Thank you so much for an amazing talk, following on us looking at pictures from way back, of course, before even the technology of writing, as it were, to now seeing these global images of precipitation. It just gives us goosebumps. So thank you so much. There are some questions for you in the chat, and if you would be so kind as to respond to them in the chat, that would be absolutely fantastic.
Yep. Okay.
Thank you very much. Now we're going to be moving on to learning about what you can do, what you can be doing at home in your yard to better understand precipitation and to help be adding to this repository of open science data. So we will move next to Newman, who is going to be joining us and telling us how you can use these very inexpensive rain gauges. I, as a matter of fact, have one in my front yard, and I collect data for CoCoRaHS, and how you can be helping to not only be measuring this so that we can compare and contrast what we're getting and what they're getting, say, across the street, but also it helps you to be keeping track of how much precipitation is falling in your area. And is that more? Is that less? It's something I've learned a lot about by having my own rain gauge. It's one thing to hear that we had 1/2 inch of precipitation fall, but by actually looking at it in my gauge and experiencing it, it means so much more. And this is like a $30 to $40 piece of equipment that is so easy to just put out in your yard. So I'm going to stop gushing, and Noah, it's all yours.
Thank you so much, Dorian. I really appreciate that introduction, and I am thrilled and honored to be speaking to this group today. So thanks to NASA, thanks to GPM, congratulations to you guys, and thank you to our home institution, CoCoRaHS, and funded by NOAA's Office of Education, and our, again, home institution, CIRA, under the umbrella of Colorado State University. So our acronym is a funny one, CoCoRaHS, but the 3 primary letters besides community collaborative are rain, hail, and snow. And so those are the primary things that we are measuring in our network. The one and only requirement for our volunteers is to use the same type of rain gauge that everyone else is using. This is a manual gauge, so it takes a person to actually physically take the measurement and empty it on a daily basis. And I would also add that if many of you out there might have automated equipment, such as a nice weather station that you've mounted to your roof, and those are great, but unfortunately the ways that they measure precipitation are sometimes, especially in wintertime, can fail. And so we really are trying to stick to everyone using the exact same type of rain gauge in our network. Now, CoCoRaHS started after a flood event that occurred in Colorado in 1997, and where a good, in fact, nearly a whole year's worth of rainfall fell in one part of the town, but not the part of town actually where most of the damage occurred. So that was quite interesting in its own right. The problem that we're really trying to solve is the thing that many of us have experienced just looking out the window, where it can rain nearly across the street and not on you. And so the more volunteers that we can get to put out a rain gauge, the more we can understand that variability of precipitation. So back in 1997, how did it get done? How did we know that the west side of town received a whole year's worth of precipitation after this event? But the only rain gauge in town recorded about 2 inches of rain. These are not elevation, these are inches of rainfall for this event. And what took place was what was called a bucket survey, literally going around and knocking on people's doors and asking them if they had a bucket in their backyard. We would take a ruler and measure it, and that was as good as we could get, but it would take a long time to complete. And now, as CoCoRaHS has evolved even through today, this is a today's map of the Denver metro area where we're looking at snowfall totals. And you can really see some of the variability of on the eastern part of the city, only 1 inch, all the way upwards of over 30 inches west of Denver. So variability is what we're really trying to track here. And it's easy to be done with a simple rain gauge that you can put in your backyard. So over all these years, we currently have 25,000 active stations. We get about 14, maybe 15,000 reports every single day. And since 1998, we're closing in on actually 72 million records, which is, we're very proud of that. And it's created not only robust weather records from day to day, but now we're getting into all these many years turns into, you're looking at potential climate research as well. So who uses our data? The list is long, but the primary user is the National Weather Service. And many of the products that they produce that go out to the public have CoCoRaHS data embedded within the totals that you may see for your precipitation in your city. It's really easy to be a part of it. If you join and get yourself registered, you can enter data on the website, or there's a smartphone app. It takes, we say, 5 minutes a day, but oftentimes even less than that. And you've contributed your report to science. You do not have to do it every single day, but the more consistent you are, the better. This is one of my favorite graphs to show people that, and to remind you that weather is not climate. And especially when it comes to precipitation, not only because is it going to rain different across the street than where you are, but from 1 year to the next. This is over 100 years of annual rainfall data from one location. And what I would say to people who set up a rain gauge and start participating with CoCoRaHS is to not expect to see trends in your own data. Even after 5 or 10 years, you're not going to necessarily be able to tell that it's getting wetter or drier at your particular location. But it's really fun to look at your data and be able to compare to those climate records here. And you can see these are the long-term amounts that you might be able to expect at one location for an entire month here. But what did you actually get? And you can explore the CoCoRaHS data set and find out how much people measured and how that compared to those long-term climate averages. So how can you join? It's really easy. You can go to our website. You need to get your own CoCoRaHS rain gauge. There are 2 models right now, and as Dori mentioned, the basic model is about $40, and I think the fancier model is maybe $55. And you can self-train. Just make sure you put it in the best location you can, and you can start observing and submitting your data. I would add, because we've got an international audience tonight, that unfortunately CoCoRaHS is only available in the United States and Canada, but it is the exact same rain gauge that the GLOBE program uses, which is worldwide. And so the next speaker, I believe, is with the GLOBE program. And although she's going to be talking about cloud observations, if you're in an international location outside of the United States and want to do something just like CoCoRaHS, you can look into the GLOBE program and participate with this exact same rain gauge. So with that, thank you so much. And you can contact me, Noah, at CoCoRaHS.org, or go to our website, and I'm happy to answer questions afterwards or by email. So thank you so much.
Thank you very much, Noah, and thank you also for putting a plug in, a seamless kind of a plug into the next speaker. And we've been having some questions in the chat, so if you'll take a look at the chat and feel free to jump in there. I also put in a link for this resource packet or story map that I've made, and in there I have the link to CoCoRaHS, information about it, an introductory video, and then also some information on what Marilé Colón Robles is going to be telling us about now, and that is the GLOBE program. So without further ado, please jump on in.
Thank you so much. Hello, everybody. My name is Marilé Colón Robles, and as Noah said, thank you, Noah. I am part of the GLOW program. I'm gonna share my slides here. And I love talking about this topic because I'm from San Juan, Puerto Rico. So I grew up by the beach looking at sharks. And that's my favorite type of shark right there. And lizards, I love lizards. And now there's a lot of green iguanas in Puerto Rico, and they swim all around you as well. So very happy to be here in a plug because my mom was in the US Coast Guard. So I've always been in the water studying storms and even playing music about storms like Vivaldi. And so the GLOW program has been around since 1995 when teachers and scientists came together on ways that students and now the general public can make observations about their environment. And there's multiple ways that you can make measurements within the atmosphere, biosphere, pedosphere, and hydrosphere. It is NASA's largest and longest lasting citizen science program about the Earth. It's supported by NOAA, NSF, and the US Department of State, and it's implemented at UCAR. Currently, we have 127 different countries participating. So as Noah said, if you would like to make observations from your country, you can look into the GLOW program. Now, I have always been fascinated by clouds, especially hurricanes. We were talking about hurricanes, and I lived a little bit in the Midwest and when storm chasing and things like that. And I'm hoping that everybody that's in Oklahoma and Texas is safe because today is a very active day with severe weather. But I hope that you know and you've seen if you look up at clouds that not all clouds are the same. And not all clouds cast shadows. And when you see a shadow, it really is when the clouds are blocking that light from the sun. And it gives us an idea of how it's interacting with the light from the sun. But also, not all clouds produce rain or snow. So a big question, hello Larissa, I see you in the chat, is how many clouds do produce rain or snow? So if we look at the types of clouds and the names that the clouds have, how many cloud types produce rain, snow, or what we call precipitation, graupel, things like that? You can use the chat if you want to try and guess. So how many clouds? How many clouds? Is it a whole 10 clouds, 5 clouds? I think I saw the answer. Two-ish is, yeah, it's actually 2. So cumulonimbus, which is the thunderstorm, my favorite type of cloud, and then the nimbus stratus cloud. So knowing that and understand the importance of keeping track of these clouds from both the satellite's perspective, but also from our perspective. So let's do a little bit of clouds. You can do a little dance with me. You can find me online, and I love to do the cloud dance. But cumulus is the first type of cloud. These are the ones that I have hanging around me. The air is moving upwards in them, and I like to tell the kids to move their hands like this, and you can do it with me if you want to try and stretch out. But that's how you see these towers and these clouds, and if you keep doing it more and more, you'll develop a thunderstorm. Stratus cloud, stratus means layer, so these are flat but in every direction, and you can stretch out with me and make those stratus clouds. You see them on the west coast of the continents. And then the third main type is the cirrus clouds. So these are the highest clouds. They're always made of ice crystals, and then these are nice and thin. So once you know these 3 types, cumulus, stratus, and then cirrus, then you can understand or start identifying the types of clouds. Now, I'm a part of a team at NASA Langley Research Center here in Hampton, Virginia, very first of all the NASA centers, that when you make a cloud observation through the GLOW program, will match it or compare it to satellite data and send you, get this, send you a NASA personalized email. Yes, you will get a email from NASA with a link to a table that has your observations and all the satellite data. And then the picture that the satellite took will be centered on your location. And so we use geostationary satellites, which are the ones that are used for weather, and then low Earth orbiting satellites like NOAA 20 or Terra. And so if you go outside and make an observation while it's daylight, within 24 hours, you will start getting these emails and these comparisons. And so how can you do that? The easiest way is to download the Globe Observer app. It is free to download. It's available in multiple languages. And then you can start by making cloud observations. When you go into the clouds, you can look at the number of observations you've gotten. We now have streaks and badges. You can look at when the different satellites will be above your area, and then plan your observations if that's something that you want to do. Set yourself reminders or alerts of when that's going to happen. You can find cloud charts and other things too, as well as other people's observations of clouds. It's really neat. And we are getting cloud observations from every single continent. And yes, that includes Antarctica. Right now, there are expeditions over the ocean into Antarctica, and you can see those cloud observations as well. Now, something that's going to happen really soon, and it's so exciting, is a total solar eclipse from Mexico all the way to Canada. And this is going to affect the clouds. So we are excited if you would be willing to make observations about an hour before your maximum of the eclipse to an hour after. You do not have to be in the path of totality. But something that'll happen is, because we're in a solar powered Earth, as the moon covers the sun, which is what an eclipse is, the air temperature is going to change, and you might start feeling a coolness to the temperature. The clouds, depending on the type of cloud, especially those cumulus clouds, remember our dance, those are going to start dissipating or disappearing as the eclipse happens. And then the wind might pick up, the elusive eclipse wind, which I felt when I was at the 2017 and then the 2023 annular eclipse at about 80 to 85% totality. So it's really neat to start noticing those differences, but also to measure them so that you can see how the temperature is changing, how the clouds are changing. So tomorrow we are starting our Globe Eclipse Challenge, Clouds in Our Solar Powered Earth. We invite you to make observations from March 15th through April 15th of clouds, and start getting ready if you're going to be between the areas that are going to experience the total solar eclipse, and then make observations on that day on April 8th, 2024. And we're going to be using those observations to study how clouds are changing or change during the eclipse in different climate regions. If you see the path of the eclipse, it's going to pass through different climate regions. So we really want to study that. And then we're going to hold a webinar similar to this one, but about the eclipse and about clouds, that you are more welcome to join and learn more and talk to me and other scientists. So I'm going to pass it back to Dorian, and thank you so much, everybody, for inviting me over.
Wow, thank you so much. It really is amazing to be able to go from, looking way out to, we're looking back to the past, and then also looking to what we're able to do right now, and getting a sense of how, we can be involved? What can we do to be a part of this? So what I wanted to finish up with is to thank all of our amazing, talented bench of speakers who came here tonight, and also to thank all of you participants. We've had 150 people on this webinar. That's super, super impressive. And what I want to share with you is something so that if some of this tastes like more, and you want to go away and you say, I'd love to know a little more about any of these topics, this resource packet or this website that I've created for you has information on the webinar that we were just on here. And then as you go through it, it also will teach you about Earth's water, lots of different resources about how at NASA we study water, and also how important water is to us. Then we'll go even closer into freshwater. 73% of our beautiful home planet is covered by water, and yet less than 3% of that is freshwater. And most of the fresh water that we use to meet our needs is actually from precipitation. So you're going to learn more about that in this resource packet. It's just kind of like homework in a way, but really, really cool homework. Then you get to learn about the GPM mission, Global Precipitation Measurement Mission, that Chris Kidd was talking about. And you can just dig in there and find out a lot of things. One of the things that I find absolutely fascinating working with this project has been something that both Andrea Portier, who's running behind the scenes here with us, and I worked a lot on, and that is learning about the people who are using the GPM data. So if you come and click here, who uses GPM data, that's going to give you some deep dives into a lot of the different ways in which these data are being used to improve life all over this home planet. And then, of course, CoCoRaHS wanted to, we've got the website here and a video and lots of really, really good information. It's really a nice group of people to belong to. And as Noah said, it's not a huge ask. If you're gone and you don't put your data in there, no problem. But another thing I find really neat is I'll put my data in, and let's say I have 0.87, and you're looking at that in my case in inches. And then I want to see how many people around me had the same amount. What are the differing amounts? I can go and look at a map and I can see other people right in my area or anywhere in the United States or Canada and see right away what they found. So that's really cool. The GLOBE program, I can't say enough good things about it. As Marilé said, it is in 127 different countries. I mean, how cool is that? You can go here and learn about the GLOBE program in and of itself, and then learn more about Globe Observer, which you just use your smartphone, trying to get my smartphone in here, your smartphone technology. And right now you're not going to see the eclipse, but for those of you who are on even off of the eclipse path, but somewhere near it, that is going to show up next week as a practice, and then you can use that during the eclipse. So there are so many ways for you to get involved and be involved. And we are just thrilled that you came and you joined us this evening. Huge thanks to Noah, to Marilé, to John, to Chris, to Andrea, to Ebony. It takes a real team to make this happen. And also to all of you for caring, for being involved. And I will remain on in case there are any questions. We will go ahead in just a second here and we'll stop the recording.